In geotechnical engineering, understanding the properties of soil is essential in ensuring the stability and safety of structures. One of the first and most crucial steps in this process is the collection of undisturbed soil samples from the field. These samples allow engineers to study the soil in its natural state, maintaining its structure, moisture, and density for accurate laboratory testing. The collection of undisturbed soil samples is a fundamental part of geotechnical engineering investigations. It bridges the gap between field conditions and laboratory analysis, allowing engineers to design safer and more reliable structures. Through careful sampling, accurate testing, and sound interpretation, the true behavior of soil can be understood, ensuring the success of every engineering project. Soil sampling. Soil sampling is a vital part of geotechnical engineering. It allows engineers to study the ground beneath a site and understand its natural properties. Through sampling, we can identify the type and condition of the soil, information that is essential for safe and effective foundation design. By obtaining undisturbed samples, the soil's natural structure and moisture are preserved, allowing for accurate laboratory testing. These tests determine important properties such as strength, compressibility, and bearing capacity, all of which influence how a structure will perform over time.
Two types of soil samples. The first one is the disturbed sample. The natural structure of the soil is altered during the collection. It is used for tests like grain size, moisture content, and classification. And the other one is the undisturbed sample. The soil's natural structure is preserved. It is used for strength, compressibility, and permeability tests that require the soil to stay in its original state.
An overview of the different tools used in soil sampling. First is hand auger. A hand auger is used to drill manually into the ground to get soil from deeper layers. It allows accurate sampling at different depths without heavy machinery. Second is core sampler. A core sampler collects undisturbed soil inside a cylindrical tube, keeping its natural structure and moisture intact. This is important for laboratory tests such as permeability, porosity, and density. Third is split spoon sampler. The split spoon sampler is used in standard penetration tests for geotechnical projects. It collects samples from deeper layers even through harder soils. It helps engineers study the soil's strength and bearing capacity for foundation design. The soil sampling process starts with proper site preparation to ensure accurate and reliable samples. During this stage, the area is cleared of unnecessary debris, rocks, and vegetation up to about 30 meters deep to expose the natural soil surface. After clearing, the location is marked with a 12 by 12 inches square, which serves as the exact sampling point. This helps make the sampling more organized and ensures that the soil taken truly represents the ground condition. For undisturbed soil sampling, after carefully extracting the soil sample using tools like a Shelby tube or core sampler, the sample is sealed tightly with cling wrap to preserve its natural structure and moisture. This prevents contamination and drying, keeping the sample in its original condition for testing.
After collecting soil samples, we take it to the laboratory for experimenting. First, visual classification of soils. This test involves a qualitative assessment of soil properties through direct observations. The students describe soil texture, color, structure, particle size, and angularity. This test develops an understanding of soil identification and classification based on visual and tactile observation. Second, basic soil assessment using soil survey instrument. The students use 4-in-1 soil survey instrument allows for rapid insight evaluation of soil properties such as pH, moisture, temperature, and light intensity. It is commonly used in agricultural and environmental assessments to support site suitability evaluations and decision making. Third, moisture content determination. This test determines the amount of water present in a soil sample by oven drying it and comparing its weight before and after drying. The moisture content influences strength, compaction, and permeability characteristics of the soil. Next, grain size analysis, sieve analysis. This test classifies coarse-grained soils by passing them through a set of sieves with standardized mesh sizes. It provides data for constructing grain size distribution curves used in soil classification system such as USCS. Next, grain size analysis, hydrometer analysis. For fine grain soils, hydrometer analysis measures particle size distribution based on sedimentation rates in a suspension. It helps in identifying soil types and predicting engineering behavior like compressibility and permeability.